Hi, my name is Hannah Mitchell, and I will be doing my presentation over direct circuit motors. Here is a table of contents that will be discussed in this presentation. So first, a direct circuit motor is established as a rotary electric motor that can convert mechanical energy to direct current power. The DC motor consists of a stator and a rotor, and the stator here is the magnets, and the rotor is the armature, which you can see is rotating. There are many different types of DC motors, such as shunt, series, compound, and permanent. The simplicity of the motor allows for it to exist in many household appliances, such as toys, garage door openers, standing fans, ceiling fans, and electric razors. All these must obtain a converter to run from DC to AC. So our system assumptions can be seen here. We need friction torque proportional to the shaft angular velocity. The demagnetizing effect will just be neglected. Our magnetic circuit is to be assumed linear. The rotor and shaft is assumed to be rigid. The motor torque is related to the current of the armature by a constant factor. And lastly, the back EMF is related to the rotational velocity by T and RE equations here. Here you can see a circuit for a DC motor. The DC motor here is represented by the circle in the center, which is mounted by the brushes and connected to external terminals, which then supply the voltage. On the supply terminals, the armature resistance, which is RA, is in series. Now, the input voltage, E, is applied across the brushes. Electric current, which flows through the rotor armature through the brushes, then goes to the magnetic field and produces a torque. Torque then causes the DC motor armature to rotate, which you saw in the video. As the armature conductors are carrying currents, EMF voltage, EB. The generated EMF, EB, is directed opposite to the supplied voltage and is known as the back EMF as it encounters the forward voltage. Back EMF is represented in equation 1 here. In equation 1, P is the number of poles, phi is flux per pole, Z is number of conductors, A is number of parallel paths, and N is the speed of the DC motor itself. From this equation, you can see that EB is proportional to the speed. So whenever a direct current motor rotates, it results in the generation of back EMF. Since it is proportional, when the speed of the motor is reduced, EB therefore decreases. Also seen, when there is an increased voltage difference, armature current will increase and therefore torque, and hence the speed increases. In equation 2, the armature winding electrical resistance, which is RA, is small. This motor causes this motor to have a very high starting current in the absence of back EMF. As a result, we need to use a starter for this DC motor. So once the motor is started, it continues to rotate. The back EMF then starts being generated, and gradually the current decreases as the motor picks up speed. Here we have a block diagram of our DC motor. Our EA is our input voltage, our EB is our outer, our R's and our L here is our resistance and inductance. KT is the motor torque constant. J is our moment of inertia. B is our motor friction. And then KB is our electromotive force constant. For our feedback, you can see that our torque, our motor torque, our moment of inertia, our motor friction, the resistance, and the inductance are then inserted as GS. And then for our electromotive force constant, it comes out to be HS. When we put YS over RS, we can find that GS over 1 plus GS times HS, where GS is the forward gain and our GS times HS is our loop gain. Here you can put in all our inputs with our G, and you can find your K over S TS plus 1, which goes from a second order system to a first order system. Our basic design requirements here are that we want it to rotate at a desired speed, which requires our steady state error to be less than 1%. Our next requirement is that it accelerates rather quickly, so our steady state speed will get to turn on as soon as possible, and so that results in a settling time less than 2 seconds. Our last requirement is that it has a sturdy design, therefore there is no damage to the equipment, so an overshoot of less than 5% is required. Next, we're going to talk about our open loop. The speed of rotation of the motor will depend upon the voltage supplied to the amplifier by the potentiality meter. The potentiality meter is placed on either the top or the bottom of the resistance for a DC motor. This then represents an input which is amplified to drive the DC motor at a set speed of N, representing the output of the systems. An advantage of this type of design is that it is rather cheap and simple to implement. The disadvantage of this type of design is that variations or disturbances in the system affect the speed of the motor. For my open loop response, I had specific parameters for my inertia, damping ratio, electromotive force, our resistance, and the inductance. The parameters here also must go along with the assumptions stated above. Next, for the controller design, here is a PID that is what provides a continuous variation of output within a control loop feedback mechanism to accurately control the process. The goal of a PID loop is to use data from the feedback device to adjust the output until it has reached the target value. So a settling time for a PID design would be 0.04 seconds, an overshoot of less than 16%, and no steady state error even in the presence of a step disturbance input. Here are the parameters that I used for my PID. And after putting it in MATLAB, I got this graph, the step response, and next is the root locus. So the next thing I'm going to talk about is the closed loop response. To avoid the disadvantages from the open loop design, a closed loop technique is implemented. The output measured speed is fed back to the speed controller, so there's an advantage there. The next is that a closed loop can maintain the speed by adjusting the terminal voltages. and a fine control of speed can then be obtained. Advantages for closed loop response: it has greater accuracy with the fine control of speed, improved dynamic response, motor operated at constant torque and constant speed, stabilized operations without any major deviations, and circuit protections can be incorporated into the closed loop speed control. Here are my parameters for my closed loop response. They're the inertia value, the damping ratio, the resistance and inductance were all the same for the closed loop as well as the open loop, with the addition of the Kp and the Ki values. And this is my graph for my closed loop. So in conclusion, we've discussed DC motors, how they can convert mechanical energy into direct current power, how they consist of a stator and a rotor. They are simple and can be used in many household appliances. The assumptions stated must be met and sustained for it to work properly. It can be represented in a circuit and block diagram as shown. And the requirements for a basic DC motor are very similar to the PID controller with a few alterations. The closed and open loop vary and have their own advantages. And here are my references.